Every country has a sovereign right to regulate radio frequency energy in its airspace. And when the radio frequency energy passes across public airspace, which is most of the time, and when there's contention for its use, which is all of the time, then the government is required to come up with regulations to allow rational use of this shared resource. In North America, Canada, the United States, and Mexico coordinate frequency use so that people can travel between the countries and we can buy products manufactured under the NAFTA agreement. In the rest of the world, which is called Europe in the telecom business, the International Telecommunications Union, the ITU, coordinates frequency usage between countries. The use of the term spectrum, which is a Latin word, it means image in English, is attributed to Sir Isaac Newton, who first used it to describe the rainbow colors coming out of a prism. Today we apply the term to the whole range of frequencies of electromagnetic energy. The government will identify and allocate blocks of frequencies to particular services. These allocations are divided up into allotments. An allotment is a smaller band of frequencies within the allocation, and the allotment is assigned to a user, which is usually a common carrier. Common carrier means that it's an entity that carries the traffic for multiple users on its facilities. In the United States, the FCC is responsible for managing the radio spectrum for all users except the federal government. In Canada, it's Industry Canada, which incorporates the former Department of Communications. If we take a look at this chart, starting at the lower end of the frequency spectrum, we have some allocations for what you might call obsolete or legacy technologies. There's an allocation for the first kind of cordless telephones in there that we don't really use anymore. CB radio and AM radio. AM stands for amplitude modulation. We'll take a look at this in the next lesson. And we're talking about frequencies between about 500 kilohertz and 1500 kilohertz there. So we're talking around 1 megahertz for AM radio. Then there's an allocation for television broadcast, channels 2 through 6. Then a gap for FM radio. We're talking about frequencies around 100 megahertz for FM radio. And then channels 7 through 13. Then there's an allocation for maritime VHF, very high frequency radio, around 450 megahertz. And after that was an allocation for UHF television, ultra high frequency. And these would be the channels 14 and above. Attaching a loop antenna to the back of the television set and facing it towards the transmitter, it was possible to detect a radio carrier frequency that was being varied to represent or be an analog of the value of light intensity detected by a camera scanning left to right, line after line, top of picture to bottom picture, and repeating. The radio carrier frequency is varied in time, mimicking the output of the scanning camera as it changes in time. The size of the picture and the speed at which the scan is repeated determines the channel bandwidth required. The energy of the radio waves that are absorbed by the metal of the antenna induces electrons to move in the metal, causing a continuously varying electrical voltage on wires attached to the antenna. This voltage is again an analog of the light intensity detected by the scanning camera. The antenna's wires are connected to a tuner in the television set. The tuner converts the voltage varying at the radio channel frequencies to voltage varying at normal or baseband frequencies. This voltage is used to vary the intensity of a cathode ray gun, a device that produces a focused beam of electrons pointed at the back of a phosphorus-coated glass screen. The beam is swept left to right across the screen, line by line from top to bottom, and then repeat. Bombarded by electrons, the phosphorus emits light, recreating on the screen the camera image that is being scanned. One could imagine families eating TV dinners on TV trays, watching The Wonderful World of Disney on Sunday night on a black and white TV in 1966. As part of the transition from analog broadcast television to digital broadcast television after the beginning of this century, the frequencies for UHF channels 38 through 69 were repurposed for mobile digital communications. Because modems are employed, broadcast digital television channels can be packed more densely than channels carrying analog signals without adjacent channel interference. This enabled the movement of existing broadcasters on channels 38 through 69 to the frequencies below channel 37, below 614 MHz, in a process called repackaging. The band 614 to 698 MHz, formerly called UHF channels 38 through 51, is now referred to as the 600 MHz band. The band 698 to 806 MHz, formerly UHF channels 52 through 69, is the 700 MHz band. Television is one-way communications. Phone calls and internet access, of course, require two-way simultaneous connections, sometimes called full duplex. Using different frequencies for the base station's transmitter and the mobile's transmitter to allow two-way simultaneous communications is called frequency division duplexing, FDD. The alternative is to assign the same frequency to the base station and the mobile and have them alternate transmitting in time, called time division duplexing, TDD, also known as half duplex. The 600 MHz band was reallocated, as shown in the figure, to create 7 paired 5 MHz blocks. 5 MHz for the base station for downloading, and 5 MHz for the handsets for uploading. This is abbreviated as 5 plus 5. The number of bits that can be communicated, called the capacity, is proportional to the width of the frequency band that's available for use. 5 MHz of bandwidth is not sufficient for providing broadband wireless, for example 50 megabits per second per user, to multiple members of the public at the same time.
Laurel Lane's one of our big problem areas right now. Everyone's sharing the internet. Hence, they slow each other down and they get a little nuts.
Funny stuff, Johnson, funny stuff.
Now it's pretty crazy. It's like every man for himself.
Drop the mouse, son!
People try to take the law into their own hands.
Drop the mouse!
And then we have to step in and start cracking down a little bit.
Whoa.
It's almost to the point of being totally out of control.
So how long were you on the internet tonight?
20 minutes. 20 hours! 20 hours!
The connection's too slow, and everybody starts getting annoyed. So what we've had to do is we've had to restrict it.
It's 6:30, folks. Odd numbers. Please log off.
Everybody got a computer. That was okay. Everybody wanted to get on the internet. That was okay. Everybody wanted to get on the internet at the same time.
You're ruining it! You know you're ruining it! Log off!
Not a good thing.
Multi-user broadband is implemented at higher frequencies with channels 20 to 100 MHz wide. However, radio in the 600 MHz band enjoys transmission characteristics like range and in-building penetration that are far superior to systems at higher frequencies. This makes the 600 MHz spectrum ideal for Internet of Things applications like trackers and monitors, where the data rate requirement is low and wide coverage and excellent in-building penetration is desired. After being repurposed from UHF channels 52 through 69, the 700 MHz band was organized into the lower 700 MHz band and the upper 700 MHz band due to differing statutory requirements and differing levels of incumbency, as there were approximately 10 times more existing broadcast license holders in the lower than the upper. In North America, the lower 700 MHz band was reallocated to 3 blocks of 6 plus 6 MHz, plus 2 unpaired blocks. Fixed, mobile, and broadcast services are permitted in this spectrum. In the rest of the world, which as we said is called Europe in the telecom business, the increasingly inaccurately named Third Generation Partnership Project, 3GPP, defines different bands. Band class 12, which covers the A, B, and C blocks, and band class 17, which covers B and C only. Allowing all carriers' customers to roam on a 700 MHz spectrum allotment was a condition for licenses in both the US and Canada. The Canadian regulator specified this in a document sensibly titled Conditions of License for Mandatory Roaming and Antenna and Site Sharing and to Prohibit Exclusive Site Arrangements. There was a lot of interest in the 700 MHz band because, as we're going to see, as the frequency decreases, the penetration through walls and the refraction around objects is a lot better. And so carriers looking to provide services over longer distances and inside the home are quite interested in getting these 700 MHz frequencies. The upper 700 MHz band was allocated as matched blocks of upload and download spectrum, with block C at 11 plus 11 MHz, block D 5 plus 5, blocks A and B at 1 plus 1, plus 12 plus 12 MHz for public safety. During the 9/11 terrorist attack on the United States, it became clear that there were significant problems with mobile communications for public safety personnel. It was very difficult to get cellular service during the emergency. It was difficult, if not impossible, to communicate different agencies like FBI, fire, and police, and they could not roam on each other's private radio systems. Telecommunications networks are overbooked. There are far more users than there is capacity to serve them all at the same time. This is called statistical multiplexing, exploiting the fact that not all users, statistically speaking, will be communicating at any given time. Users get the possibility of communicating for a lower price than were capacity provisioned for each user, whether they were transmitting or not. The amount of overbooking is based on historical demand statistics. However, during a crisis, when everyone does try to use their wireless service at the same time, the demand is far higher than usual and there is a capacity failure. Public mobile communications networks cannot be relied upon during an emergency.
Due to the earthquake in the area you are calling, your call cannot be completed at this time. Please try your call later. 092T.
The solution was to build a nationwide separate network for public safety use, where it was possible to control how many people have access and thus avoid loading failure. The U.S. Congress required the reservation of the 12 plus 12 public safety block in the upper 700 MHz nationwide and created an organization called FirstNet to manage the construction and maintenance of a nationwide cellular network paid for by taxpayers and only for use by first responders and government agencies. Above 700 MHz is the 800 MHz band, not surprisingly. And when we say 800 MHz, we mean the band that goes from about 800 MHz to about 900 MHz. And this is where the first generation of cellular was deployed in North America. At 900 MHz is an unlicensed band. And what that means is that users do not need a license to produce electromagnetic energy at the frequencies specified. This is also called an Industrial, Scientific, and Medical Band, an ISM band. And this is at 900 MHz in North America. So there were a lot of systems that used this band in order not to require a license. So we had cordless phones and baby monitors at 900 MHz. 900 MHz in the rest of the world was where the first generation of cellular was deployed, and then subsequently the second generation was deployed on the 900 MHz band. This second generation of cellular, called GSM in Europe, was deployed at the 1.8 GHz or 1800 MHz band. In North America, the second generation of cellular, which we'll see was called PCS, was deployed at 1900 MHz, 1.9 GHz. Between about 1800 MHz, 1.8 GHz, And 2.4 gigahertz are many, many bands that are allocated for various generations of mobile communications. And what happens is that initially they might be deployed for a particular generation of mobile communications, like second generation GSM, for example. And then as time passes and eventually the carrier is allowed to stop providing that generation, those bands will be repurposed to a new generation technology for mobile communications. At 2.4 gigahertz is another unlicensed band, and this one is used by many different devices because you don't need a radio license to emit energy at these frequencies. Bluetooth runs at 2.4 gigahertz, so do cordless phones, and we have wireless LANs running at 2.4 gigahertz, and microwave ovens run at 2.4 gigahertz. So there's a lot going on in the 2.4 gigahertz unlicensed band, and we're certainly going to discuss that later on in the course. And there's another unlicensed band, well, actually there are a couple of them, up around 5 gigahertz. The 2.5 gigahertz band has a promising future in broadband wireless, with two 50 megahertz wide channels and one 17.5 megahertz channel available for mobile and fixed applications. The channel width has increased from 10 and 15 megahertz in the 800 and 1900 megahertz bands to 50 megahertz, dramatically increasing the capacity available. New spectrum from 3550 to 3700 megahertz, called the 3.5 gigahertz band, is beginning to be used in North America for fixed broadband wireless services, providing broadband wireless internet to residences and businesses as an alternative to cable, DSL, fiber, or a cellular data plan. This service is provided from cell towers and currently uses LTE, but it's not accessible by mobile phones. With approximately 150 megahertz of bandwidth available and channels up to 40 megahertz wide, there is capacity sufficient for multi-user broadband in the 3.5 gigahertz band. However, as frequency increases, transmission characteristics like penetration through obstacles worsens. 3.5 gigahertz energy is significantly blocked by near-field interference, usually trees in front of the antenna. Line of sight between the tower and the antenna at the customer premise is required to achieve broadband bit rates. The 3.7 to 4.2 gigahertz band was allocated to fixed satellite service space-to-earth communications and fixed services using 20 plus 20 megahertz for point-to-point long-haul analog radio telephone trunk carrier systems. Paired with the 5.925 to 6.425 gigahertz band, that's for Earth to space, these frequencies are known as the conventional or C-band in the satellite business. By repacking the incumbent license holders in the 3.7 to 4.2 gigahertz band into the upper 200 megahertz of the band, 280 megahertz of spectrum between 3.7 and 4 gigahertz will become available for broadband terrestrial 5G applications. In the US, the FCC has completed spectrum auctions in the 24 GHz band, the 28 GHz band, and the upper 37 GHz, 39, and 47 GHz bands, representing almost 5,000 MHz of spectrum for 5G, 200 times more than the bandwidth that was allocated for 1G. The bands around 30 GHz are called millimeter-wave bands, since the wavelength of the energy is measured in millimeters at this frequency. But at these frequencies, molecules in the air block energy, a phenomenon called atmospheric absorption, which limits the useful range to hundreds of meters. One application for 5G data is data communications for assisted driving cars, where a central controller assembles cars on the highway into convoys or platoons to increase density and reduce energy usage. Since line of sight is required and atmospheric absorption limits range to hundreds of meters, full coverage on a highway at 30 gigahertz would require radio base stations installed at about the same spacing as streetlights all the way along a highway. Like everything else in this world, there are trade-offs. As we increase the frequency, the capacity increases because by definition, as the center frequency of the band increases, then the width of the frequency band that we can use around that center frequency by definition increases. But you have to basically have line of sight at 5 gigahertz. You have to be able to see the other antenna because the transmission characteristics are not as good in terms of penetration through walls and refraction around obstacles. If we lower the frequency, then the in-building penetration and refraction around obstacles gets a lot better, but the width of the frequency band gets smaller. So it's a trade-off between capacity and transmission characteristics.